there. The very best second-party tests have public agencies similar to NJCAT that closely monitor site selection, and they assure that the proper protocols are followed. Is lab or field testing best? Well, they both have their weaknesses. Field testing is expensive compared to lab testing. Most manufacturers have a bunch of models to test, and it would be very expensive to test all of their models in the field. There are several standard structural BMP variations of sizing and geometry that need to be tested. And particle size definitions change by region, by site usage, by season, by antecedent conditions. In other words, whether it's rained recently on the site. So all these factors would require multiple field tests and multiple repetitions to reach a certain degree of certainty. And all tests are not equal. One field test is just one basin with a few storms, and like 15 storms or ATV tests in Griffin, Georgia. Field site conditions vary tremendously, as does climate. A test in the state of Washington would be very different than a test in Florida, for example. Field testing methods and analysis also vary. We've seen sampling methods from grab samples to somewhat sophisticated sediment samples to things as simple as a strainer on the floor of a pipe. Analysis has been done by what's termed the TSS test, EPA 160.2 or SSC, and so there's a lot of variation in once you get the samples and how you analyze them. And in lab tests, the lab test materials vary. If you go look at the NJCAT studies, some folks used F5, some OK110, some did a mixture as things changed. NJCATs or NJDEP specified a different particle size mix, and then the analysis methods do change in the lab. Jim Malo's in the room today. He just did an excellent paper, presented an excellent paper at StormCon on the differences between EPA 160.2 termed TSS testing and SSC, which is an ASTM method. Sampling methods vary. In the lab, you can use isokinetic sampling, or you can do something similar to grab samples. Injection methods can vary, whether you're using a slurry or a dry feed. And concentrations and flows may not be constant. Some labs are very good at flow control, others not so good. The concentrations are controlled by up front, but the measured concentrations during the test may not be constant. And it's a matter of skill and sometimes almost art to keep those parameters within a reasonable variance so that you can have some confidence in what the test has done. So no matter how accurate any test, field or lab may be, the problem of testing one size device and scaling the results to apply to the test, to apply that test to other devices remains a problem. As an example, we've been very fortunate because in our testing, we tested a 9x5x6 device in the lab. Our ATV test was on a 10x5x6 device. Our South Carolina DOT test was on a 12x6 device. And our Highlands, North Carolina test was on a 20x6 device. We used the same hydraulic loading rate across each of these devices for design. And our results were quite similar to each other, which probably is, which gives us some confidence that the way we scale, which we use hydraulic loading rate, which is the ratio of flow to the footprint. But there are all sorts of scaling methodologies out there where someone will test one device at the bottom of their group of sizes and then project that up, sometimes in a linear way, sometimes exponentially to bigger devices, or test a device in the middle. So how you scale can be a real problem as taking the results of a test and trying to apply it. Going back to the field testing technical challenges. How do you accurately sample flow, a pipe underflow? Because as the flow changes, the location of the sediments and sometimes the stratification of the sediments in the pipe changes. Also, the same flow in the beginning of a storm may carry different sediment particle size distribution than a flow later. Perhaps many of the small particles have washed off. So sampling a pipe under flow is a real challenge. And the labs carefully select their sampling points. They usually use multiple sampling points. If they know they're feeding in, say, 200 milligrams per liter, they can measure to see if their samples indicate 200 milligrams per liter and make some changes there. But in the field, it's a different story. So how many sample points do you have in the field? How do you adjust for different flows? Do you sample high or middle or low in the water column? Do you move it? Do you move those sample points based on the flow? Is it really possible to get an automated sampler to take a representative sample? Would a grab sample be better? I'm being a little facetious here with the sample location selection tool, but often that seems to be the way it's done. We've gone out and looked and seen strainers lying on the bottom of a pipe where your common sense would tell you they might oversample the amount of sediment in the pipe. But these automated samplers are placed in by some methodology. Usually it's not a very good methodology. Well, when do you sample a storm? That's an important point. Do you sample at low flows, at rising flows, at peaks, at falling flows? And how can you predict before the storm how long the storm will last? Everyone's familiar with how rainfall works. You've seen it rain across the street and not on your side of the street. You've seen the changes in intensity from moment to moment. And when a storm starts, it's hard to predict when you're going to sample that storm. Radar today has helped us a lot, Doppler radar and estimating rainfall peaks. There's some intelligent sampling algorithms out there that are literally real time that's going to improve that over time. But once you do get a sample, how can you be sure that that little period you sampled represented the portion of the storm when it's taken? The great Carnac would have a hard time predicting the answer of when to sample, and we draw up storms as engineers really nicely with a rational hydrograph or a SCS TR55 type of hydrograph with it building and peaking and falling off. So at the bottom you see a real storm on the bottom right hand side. This is some telemetry data from a storm in our Griffin, Georgia test. That's the real challenge in sampling. I always put these warnings on my math slides because the fine print's a little tough to read and you might not want to pay much attention to it. But remember or think about how many people have approved our product because we have a 89% removal rating at our ETV test in Griffin, Georgia, which I'm thankful for. We believe in the lab loaded with our devices loaded at about an average of 17 gallons a minute per square foot. We can remove over 80% of particle with an average diameter of about 90 microns. We think that's pretty typical of what we see in the field, although as I've mentioned earlier it changes. But if you think about what they tested, we had a little over 7.5 inches of rainfall fall on 4 acres. I did the math here for you to let you know that was a little over 110,000 cubic feet of rainfall. We figure that 3/4 of that rainfall washed off of that particular site. And to make a long story short, we had a little over 2,350,000 liters. Now they sampled 8 bottles per storm at 1.8 liters per bottle. So we had 216 liters of that amount sampled. So 0.0092%, or if you want to take it out of percent, 0.0000917 and some change of our water was actually tested, far below 0.1%, under 1/100%. Yet we reached the grand conclusion that the Crystal Stream device is a device that can remove 90% of materials from stormwater. Again, the field testing, the laboratory testing has helped us understand this, and believe it's fairly accurate. And we'll talk a little bit about that as we go along here. Field testing challenges, more field testing challenges. One of the problems that was encountered in some of the earlier studies is they had upstream and downstream flow meters. This is very important on a large BMP like a pond, or an extended detention, underground detention, or a constructed wetland where there's a lag between the water entering the BMP and exiting the BMP. I can assure you that a 5 by 10 vault with 3 CFS coming into the vault will have right at 3 CFS coming out of the vault. There's just no storage in these small structural BMPs. Nevertheless, the flow meters upstream and downstream in test after test read vastly different numbers. Well, this and here the red is the upstream flow data, the blue is the downstream flow data, and the white is the rational calculation. If we were taking the rainfall off the tipping gauge and saying, well, this is how it should work, the white would be what we would expect as engineers. Now, there are some places in these graphs that follow each other fairly closely, but it's pretty disturbing if you look at the graph on the left, where the upstream data in red shows flows at approximately half the downstream data. So there was half the water coming in the device that was coming out. It's interesting also to notice that that's not consistent which one tracks above the other. There are some things that can fool flow meters, obviously, and if you don't have good flow data, this is flow-weighted removal. So, and we'll talk about that a little bit in a second, but if you don't have the right flows to do a flow-weighted calculation, it's a little crazy. Here's a field testing challenge. I asked for and was given the minute-to-minute telemetry, or the recording of the data at these samplers. And part of what was given to me was charts that showed me not only the characteristics of the storm, and this is the velocity of the water, the level of the water, the rainfall, the flow in gallons per minute, but we also got when successful samples were taken. This 18-bottle sampler here appears to have taken hundreds, well, not hundreds, about 100 samples. No one, and this test, by the way, was used, and I've never gotten a really good explanation from a test operator of exactly when they decided the samples were actually taken. If you look at the end, you'll see a string of green dots as if sample after sample after sample were taken. Not knowing when the sample was taken makes it very difficult to calculate flow-weighted data. Now, the reason flow-weighted data is important is there's more water that goes through at a higher flow. And so if you removed, if you removed a certain amount at that high flow and another amount at a low flow, you don't average those two values. You flow weight it because the amount of material coming down in milligrams per liter, the concentration, would be more weight of material in the higher flows, well, depending on the concentration. So that's a challenge also. Here at our test, the test equipment downstream of our device was near a side pipe, and that side pipe was in the sag of about a 6-acre basin. Well, there was a slight slope upward reported on the effluent pipe out of my device, which would affect the depth of the flow, which would affect a flow meter that depended on depth for deciding how fast the water was going. And we were concerned, highly concerned. We raised the question and were assured that it was not an issue, but we still raised the question. And today I would question whether or not there was an influence from this downstream flow backwatering or flowing back upstream from our downstream testing point. To me, it could explain some of the differences. However, some of the differences went in the wrong direction. So it doesn't explain all of them. In the lab, this is a picture of, in Alden Labs, of our device being tested. It's hard to see, but in the bright monitor, there's a line where the test operators constantly monitor the flow going into our device, with the idea, if they're testing at 2 cubic feet per second, to keep that flow right at 2 cubic feet per second so the test is accurate. And that's good. because we get, in that way, we get removal curves, efficiency curves at half a CFS and 1, 1.5, 2, 2.5, whatever speeds that were chosen for the test. But that lab test, stable flows are rare in the field. It's just not what we see. So we get variable particle size delivery. I'm not saying the lab test is inaccurate. I'm saying it's unable to duplicate what we see in the field. Well, mass balance can help verify the calibration of indirect testing. But typically these devices start empty. And I'll just explain mass balance real quickly. If you place 500 pounds of material into a device at 200 milligrams per liter, let's say, and then you sample, and by sampling you believe it caught 80% of that material. That's what your sampling indicated. Then at the end of the test, you stop the device, you dry the material, and you weigh it. And you should have, if you caught 80% of 500 pounds, you should have 400 pounds of material in the device. It's not absolutely necessary to start with a device empty. There are ways that you can put the device on load cells and calculate the difference in the amount. But in the field, devices are only empty for the first event they encounter. So this is, again, an excellent way of calibrating how your sampling is going. It's not necessarily indicative of what's happening in the field. When you're doing resuspension tests today and some other tests, today the new protocols are requiring these devices be loaded to 50% of capacity, more or less, when they start. Another lab testing challenge, and again, this isn't a challenge to the accuracy of the lab test. That's not what I'm talking about. I'm talking about how well it would relate to how a device would function in the field. In a lab test, you've got steady flows and particle sizes by design. That's what that's how you test the device, and it can allow you good precision on your sampling. You can check it by mass balance, and this is a perfectly good lab technique. But in the field, flows vary constantly, and particle size changes constantly. Even at the same flow, things that happen up in the basin, events that happen, can change the particle delivery. It is not it's not a level delivery. So lab testing just can't duplicate this. When we load our material into the device in the field, we have to look and see where the trash and debris and organics and oil is, and the fact is, of course, those don't exist in a lab test. The time between events that affect the type of material delivered, when we get dry sun-baked conditions or wind-blown conditions, and the time between events is highly significant for a device in the field. And this is something that we really can't duplicate in the lab because we have flocculation and settling and other things and chemical reactions that can actually occur in the field. So lab testing is not able to duplicate that. And of course, lab sediments are very different from field sediments. Lab is usually almost entirely silica, sand with a relative density of 2.65. That means it's 2.65 times as heavy as water. In the field it varies a lot, but it does include trash and organics, clay, chemicals, metals, grit, dust, plastic, some things higher density, some lower. We've seen a relative density average about 1.70 in the field. So to summarize how testing stacks up, field testing is the only way to experience natural conditions, but it cannot be expected to be reliable within accepted repeatability standards due to the chaotic nature of stormwater flows and wash-off rates. That's a long sentence, but essentially sites differ, rainfall differs. Field testing is a good thing to have. We're glad we have it. It shows a lot of things, including sustainability and maintainability and feasibility. Okay, but it has its drawbacks, and the drawbacks are you just can't do enough of it to form enough data points to have a statistically significant set and say much about the performance of a device. Lab testing cannot duplicate natural conditions at a reasonable cost. Land-based systems cannot be tested at all in the lab. So the natural question came to me of, could we use our laboratory results to verify our field results? And what would happen if we made that attempt? Field testing is the only way to get these natural conditions, but since it's not reliable, we want to ask, can we use lab testing to verify that? Well, in my mind, it's extremely important to have both laboratory and field testing for a product. The Manufacturers Association had a recent set of meetings to help rewrite the NJCAT, the NJDEP protocols. And we argued and whined about whether or not a field test was needed and if lab testing was all that was needed. And of course, as manufacturers, we want to know how our devices work. That can be done with a laboratory test. But a lot of us want to avoid field tests. And let me explain to you, you can't order a $500,000 third-party field test. Remember, a third party means someone else paid for it. We've been fortunate enough to have several of them. We've had 4 now. But you can't make someone pay $500,000 to test your device. So a field test, a second-party field test, similar to NJDEP's program, TARP program, is important because you still are getting field tested, even though it's somewhat under the control of the manufacturer. Well, if the laboratory test has removal curves for a known gradation of material, it's possible to apply those to a field test. Now, this requires that the rainfall and flow data from the field test is available. Quite often, it is not. It was not available in my test until I made a direct request for it. There was considerable debate. I don't think they wanted me to see that there were 150 sample points in one storm that was supposed to sample 18. I'm not accusing anybody of a cover-up. I'm just saying field test data can be dirty and nasty looking. Failed samples, beakers dropped in the lab. There's just a ton of things that can affect that data. Samples held too long, samples contaminated, failure to follow the QA/QC, quality assurance, quality control. There's a ton of things can mess that up, okay? But you got to have your rainfall and flow data. And so I made the initial assumption, that our lab test material was similar to the field material. Well, it turns out it was pretty similar based on the gradation that NJDEP is using now, and also based on the influent gradations I've seen. I've taken a lot of these tests and looked at what came into the devices. Usually it's about 50% sand, maybe 55. Usually it's about 40 to 45% silt and 5 to 10% clay. Clay, I've never really seen clay all the way up to 10, but I've seen some tests that occasionally that it would show that a clay content has. So essentially what we're saying is, let's pretend for a minute that the Alden lab material that was fed to my device was pretty similar to the field material. Well, I studied the field storms in 5-minute intervals to get the average flow for those 5 minutes. In a 4-hour storm, then we would have 12 periods per storm, or 48 periods to take the average flow in. I take that removal rate for that flow off of the curve that was produced by Alden. When the flow is faster, we remove less. When the flow is smaller, we remove more. So that's how I kind of went at the problem. Just so you know, I want you to understand that this data came from a CST water quality vault tested at Alden Labs. It was tested to establish removal efficiency curves and resuspension rates. So I took 2 standard hydrograph storms first, Rational and SCS, and the recorded storm set, full set of storms from our ETV test in Griffin, Georgia. The OK110 that was provided to us at Alden turned out to be what I call OK90, starting over on the left side over here. Is a material that was 180 microns, and then 125. This is 190, 75, and down to 60 and 50s and the fines that went to the pan. The blue is what the material should have been. There should have been a peak of material around 108 microns, 110 microns. In reality, our material peaked around 90 microns, and so our material was lighter, if you will, than what would normally be specified. These two performance curves were developed by Alden, and one of them is indirect sampling. That was pulling samples above and below the unit, determining the efficiency. Then the direct sampling was what we would call mass balance. This is a check against the indirect sampling, calibrating to make sure that that material worked well. Another little bit of math here, but we have to do some of this. If you get a higher flow, for example, if we have 70% efficiency at 2 CFS and we have 90% efficiency at 0.1 CFS and we average those two, the average is not 80% efficiency because there was a lot more water. The 2 CFS is 20 times as much water and 20 times as much material going through as the 0.1 CFS. So you weight it by the flow. So the average of 70% and 90% efficiency at those two flows is 70.95%, not 80. And I want to make that point because it's important as we go through looking at these storms to see how efficiency is affected by flow velocity. This is a peak water quality flow storm of 1.78 CFS. If you go to the Georgia Water Quality Manual and you do the math on a 1 acre site that's totally impervious, you will find the water quality peak flow is 1.78 CFS. So I use that storm as an example here. The blue line is the flow at the storm based on the rainfall and that falls into the basin. The dark blue line is our removal efficiency. If you'll notice, at the peak water quality flow in Georgia, we're somewhere around, according to the lab, about 0.62% removal. However, for most of the storm, we're well over 80% removal, but we dip down as the storm flow goes up. If we flow weight average the storm, we are at 82.5% removal, looking at a really simple rational hydrograph. Well, Georgia doesn't like to use the rational hydrograph. The theory in Georgia is that SCS hydrographs produce larger ponds and are more accurate to look at the long picture. And so I did the same storm with a peak flow of 1.78 CFS, and our removal efficiency, because of the shape of the storm here, was much better at 90.39%. This is closer to our ETV number if we do a flow weighted average of our performance. Well, I had to do an average here of the upstream and downstream flows. We mentioned this earlier. For full disclosure, I want you to know if we had used the downstream flows exclusively or the upstream flows exclusively, you'll see later what the results would have been. But we averaged these, but we did have to look at it both ways because the flows were so different. This is the same storm, and over here is upstream flow data, downstream flow data. This is just one sample event, and this shows the difficulty of taking field data and interpreting it. One of the problems was that according to the upstream flow meter, the storm was 25 minutes long, but according to the downstream flow meter, it was 50 minutes long. So the machine ran 25 minutes, apparently, after it stopped raining. I would say that there was probably a problem with the upstream flow meter if you look how this data just truncated as opposed to tapering off as the downstream meter did. But here in these two, in this example, you can see that our removal rate during this storm was plotted here in the yellow, in yellow, that's the removal rate, and then the removal rate was plotted in blue. They're not all that different for this storm, depending on where we look. So with that being said, and this is another more typical storm. Same colors, but essentially we're showing the downstream flow dark down here. And obviously the downstream removal dips as the flow goes up. The upstream flow had a huge peak in it according to the flow meter, and our removal rate was adjusted accordingly. At the end of the day, the answer really looks bad, but this is what the answer was, so I'll explain this to you a little bit. The ETV study divided what came to our unit into sand and fine material. The yellow line, which is covered over here, but this represents the sand removal efficiency for each one of these storms. Remembering that they said we were 89% total. The purple down here is the fine material removal rate, which they showed us actually a negative removal rate. 0 in one storm, a negative removal rate in another storm, which is fine. That's the way field testing goes. But it is interesting to look at the calibrated, the blue line and the red line. I'm going to follow the two of them here. They diverge a little bit here. Blue slightly better, red slightly worse. Pretty close all the way across. Actually follows that light blue sand line pretty darn closely. Of course, we were testing with sand, Oki 110 sand in the laboratory, so that makes total sense. This is a very good correlation of field data removal rates and lab data removal rates based on the removal curves that were generated at Alden. So we did the 15 events using sum of loads. We did our calculation precisely as it was done in our ETV report. Now there were 2 storms that outweighed the mass of the sediments in the 13 other storms by a large margin. So the flow data and the volume data for those storms could really push this number around a lot. In fact, if we took out one storm, our average of 89%, which hit right about here, doesn't look like this would be an average, but these 2 guys right here were real heavyweights, this one and this one. Okay, take them out, we could have been around 67% removal. All right. This is why it's so important to have that lab data out there. This is a bar chart that's just to kind of show you that graph a different way. If you take our efficiency in the method I use with the Alden lab curves, our efficiency calibrated would be 82% using the upstream data. Our calibrated efficiency would be 74 using the downstream data. ETV said we were at 89, and they said we were at 96 on the sand, and they said that we were somewhere at 79 on the fines. This is sum of loads, not actual. That's not the actual removal rate. The removal rate on the fines was 37%. By the way, and I think it's important to point this out, boy, there's a lot of things you can do with data if you want to. I caution the types of protocols that have been developed by NJCAT or NJDP, Alden Labs, and the other folks. ASTM's working on a lab testing protocol right now. It is extremely important to follow these guidelines, and everyone test and evaluate their data in the same way, so the data becomes meaningful. You can certainly do apples to apples if you test the same way and you interpret the data the same way. I will tell you that it's my belief, and it's only my belief, that a lab test that reports 80% using whatever gradation does not necessarily mean 80% performance in the field. And the fact that the EPA has allowed us to use 80% removal of sediments as a surrogate for the removal of pollutants is not significant many times, especially if nutrients are your pollutants of concern, or if there are other things such as toxicity or the need to remove metals. You need to pay close attention. But you know what? It's a good thing that we have field testing. It's a good thing we have lab testing, and that we've got protocols out there. Well, I made some conclusions here, is that we can reasonably predict field efficiency using laboratory performance curves under certain conditions. That means not to take a number, 82, and say that's what we do in the field because that's what we got in the lab. You can take a performance curve in the lab and apply it to real-time storms and storm distribution in the field. And if the materials are the same, you should have a reasonable prediction of how sediments would be collected in the field. performance curves can be developed for any lab material, including fine particle mixtures. In other words, it's not necessary to use sand only. You can use Silgasil 106 or finer materials. But if you're going to compare lab test to lab test, you need to be sure the procedures were the same, it was injected the same, the sampling was the same, and certainly the material was the same. Better influence sampling in the field can help identify proper particle size definition. I've made it a project of mine to get the influence sampling data. If I ever get a particle size definition on it, and it's been done in several areas, it was done in our test in Highlands, North Carolina, to know what's coming to these devices in the field, and to help verify what we're doing in the lab, where we're using the right particle size definition. Now, this correlation worked because the material in the basin closely matched the laboratory material. We saw with the particle size analysis, it was darn close to OK 110, although there were more fines. The fines were a relatively low percentage of the weight that went to our device, and we did a relatively poor job removing those fines. And so that's why the correlation matched up too well. There's a lot of work needs to be done on getting dependable flow meters for field testing. You may want to reference some of the work that's been done for the Department of Ecology in Washington State with their Under the Bridge DOT testing site. A lot of folks have tested for tape out there to see how they've kind of moved away from flow meters and gone to flumes and trying to find better ways to get their arms around flows. Because in lab testing, knowing the flow is everything. And I think, well, Jim Alden's here, Jim Malo's here from Alden. I think he can tell you too, in the lab, controlling your flow is everything if you're going to get a test. So the conclusion is, ideally, you need both types of tests to evaluate a BMP. Field testing can be accurate, can be variable, but it's needed to show practicality, sustainability, and maintainability. In other words, is it the right application, practicality? Sometimes putting a cartridge filter on a parking lot with a lot of paper and oil and debris is just not smart. A great machine, works good, probably needs a gross pollutant trap ahead of it, or a gravity system like ours ahead of it. Sustainability. How long is that system going to last? And this goes for land-based BMPs too. Is in-ground infiltration going to be sustainable in the high rainfalls in the Piedmont and the South? It's hard to say. There's been some outstanding sand filters, especially grass top filters. You can look at some of Gary Minton's work out in the Pacific Northwest. So practicality, sustainability, and maintainability. What does it cost to clean these things? How often do they need to be cleaned? Because you have to believe in Santa Claus, if you believe that something is going to get all of those pollutants out of your BMP magically, and they're never going to flow downstream, they're never going to leach, or worse yet, be taken up by biotics, plants, and get into the food chain. Lab testing can compare apples to apples if the same protocol is used. It also can verify scaling methods. I could say all day that HLR dominates my devices, but if I test 5 different sizes in the lab and predict with my scaling method what the removal rate should be, you can tell pretty quickly whether or not I know what I'm talking about. The best test of all is what you find in a BMP. You should have manufactured devices cleaned and see what they catch. I can't emphasize enough the fact that we have been in the cleaning business since our first device went out, and we have learned more by looking in BMPs than we ever could learn from lab tests or fluid dynamics courses or studying flow patterns and pressures inside of a BMP. Tests only indicate potential performance and verify feasibility. No BMP works for long without maintenance. I saw Boyd Church say that sand filters in Carroll County have been in place for 15 years, and that's a good thing. One of the nice things about our maintenance company, which is totally disconnected from Crystal Stream, is that we do maintain sand filters, and we're starting to find out what really works well with sand filters and what does not work so well with sand filters. And the same thing with wet ponds. Low flow, 24-hour, 48 release orifices the field performance really gives you a handle on what's good and what's bad. And I think a good motto for any BMP is trust but verify. Verification in the field is really what it's all about. So I'll be glad to take some questions now. I think the takeaway here is don't be so quick to distrust someone without a third-party field test, because you can't buy them. Literally, you can't buy them. But still, field testing is extremely important, and it could be that you ask for 10 references of materials in your of installations in your area and go look at them. Look at the pipe downstream, look at the riprap downstream or the pond downstream, look inside, get them clean, look at them again in 6 months. And that's a perfectly good field test. Not as good as a paid-for third-party scientific test, of course, but it's a way of verifying. Lab testing is certainly the apples-to-apples comparison. So I'll be glad to take some questions from you guys if you have them. Otherwise, I want to tell you I appreciate you coming. And I'm looking in the chat area for questions now.
John, thank you. Yeah, gentlemen, you can and ladies, you can either type a question in the lower corner there, or if you raise your hand and you have a mic available, we can try to free up your mic and allow you to ask the question publicly here. John, we've got one question from Boyd down there.
Yeah, I see that. A couple things, Boyd. You know, I was just with Roger Sutherland last week, and we discussed a little bit about that, about street sweeping. Part of what we've seen in the variability of our data, when I say variability, same type of site, a lot less loadings into our devices in the field. Quite often, my crews can spot sweeper marks on the curb where these sites are being cleaned by a street sweeper. And as you probably know, there are street sweepers, and then there are street sweepers. Some are brushes that kind of move the material around, do a little bit of vacuuming. Some of them are high vacuum systems. I'd refer you to the expert on that, which I think would be Roger Sutherland, where they've done some high vacuum, shop vac extraction of materials from the curb. Part of the problem is a lot of material in the street gets as in other words, it's moved by wind and not necessarily by rain. And what they sample off the street doesn't always make its way into the storm drain. It might seem obvious that it would, but that's just not necessarily so. Street sweeper sampling that's been done, that I've seen, the particle size analysis, though, has tracked very well with what's been taken out of BPs. There's a study done by St. Anthony Falls Laboratory. Omid Moshini was one of the gentlemen on that study. You could look it up. I think it's their paper 1494. And in there they had 5 or 6 studies of pollutants in watersheds. And I was surprised to see the street sweeper samples. They were a little heavier in metals than some of the others, but they tracked pretty good. So measuring sweeping streets is an excellent BMP. There's just no argument about it.